Imagine a fuel source so powerful that a tiny amount could power a city for a year. That's the promise of antimatter. Antimatter is like the mirror image of regular matter. Every particle of matter has an antimatter counterpart. When matter and antimatter meet, they annihilate each other, releasing enormous energy. This energy release is what makes antimatter so fascinating for scientists and engineers. However, harnessing this power is incredibly difficult. Antimatter is not found naturally on Earth. We have to create it in special laboratories. Even then, creating and storing antimatter is a huge challenge. It requires sophisticated equipment and techniques, pushing the boundaries of modern physics. Despite the challenges, the potential benefits of antimatter energy are too great to ignore. Scientists and engineers are working hard to overcome these obstacles. They dream of a future where antimatter could fuel spaceships, solve our energy crisis, and revolutionize many industries. It's a long and challenging journey, but the rewards could be astronomical. One of the biggest challenges with antimatter is keeping it stable and contained. Antimatter annihilates upon contact with regular matter, so storage is a major hurdle. However, scientists have made a groundbreaking discovery. They have successfully trapped and stored anti-hydrogen atoms, a major step towards potential antimatter fusion. This was achieved using a special device called a minimum magnetic field trap. This trap uses powerful magnetic fields to suspend anti-hydrogen atoms in a vacuum, preventing them from touching the container walls. In a recent breakthrough, scientists managed to trap 38 anti-hydrogen atoms for almost 0.2 seconds. While this might seem like a short time, it's a significant leap forward in the field of antimatter research. This achievement paves the way for longer confinement times and more detailed studies of anti-hydrogen. Scientists are eager to learn more about its properties and compare it to its regular hydrogen counterpart. This knowledge is crucial for unlocking the mysteries of antimatter and its potential applications. Creating anti-hydrogen is a complex and delicate process. It starts with producing antiprotons, the antimatter equivalent of protons. Scientists achieve this by smashing high-energy protons into a metal target. This process produces a shower of particles, including antiprotons. Next, scientists create positrons, the antimatter counterpart of electrons. Positrons are produced through radioactive decay of certain isotopes. Once created, both antiprotons and positrons need to be cooled down to extremely low temperatures, almost absolute zero. This cooling process is crucial for slowing down the particles, making them easier to control and trap. Finally, the cooled antiprotons and positrons are carefully brought together within the magnetic trap. Here, they combine to form anti-hydrogen atoms. The entire process requires incredible precision and control, pushing the limits of particle physics technology. Despite the significant progress, we are still a long way from antimatter-powered spaceships or cities. The amount of antimatter we can currently create and store is minuscule, and the confinement time is still very short. However, this recent breakthrough in trapping anti-hydrogen is a major step in the right direction. To make antimatter fusion a reality, scientists are focusing on two key areas. First, they are constantly improving the trapping mechanism to confine a larger number of anti-hydrogen atoms for extended periods. Second, they are exploring ways to produce antimatter more efficiently, reducing the cost and energy required for its creation. The journey towards harnessing antimatter is filled with challenges, but the potential rewards are enormous. With each new discovery, we inch closer to unlocking the incredible power of antimatter and ushering in a new era of energy production.